Alright, so let's keep on doing some examples of finding the slope implicitly. So that's another example. So let's determine the slope of the graph of three times x squared plus y squared squared equals 100xy at the point 3, 1. Alright, so let's see what we're dealing with here. So we have to take the derivative. We're going to take this derivative again implicitly with respect to x. So that means dx of 3 times x squared plus y squared squared, and well, that's equal to dx, so we're doing it on both sides, of 100xy. So that's what we're doing here. We're taking the derivative with respect to x on both sides of the equation. Alright, so remember that the derivative constant is just, well, we could use here the constant multiple rule, so we can actually pull that 3 outside of our derivative computation. So this is simply 3 times ddx of x squared plus y squared squared equals 100, we'll do the same here, 100 times ddx of xy, x times y. Okay, so let's see what happens now. So here in the first one, on the left side, we have to use the general power rule, and on the right side, we have to use the product rule. So if we do the general power rule here, we have to also use a chain rule on the inside. So 3 times that 2 is going to go in the front by the general power rule. So 3 times 2, remember minus 1 up here, so times x squared plus y squared to the power 1, because we minus 1, times the derivative of the inside. So the derivative of the inside piece, the derivative of x squared is just 2x, plus the derivative of y squared, which is 2y, and because we took the derivative of a term involving y, we put dy dx here, so times dy dx. And that's equal to, and again, we did this before by the power rule, the product rule, we're going to have 100 times the first, which is x, times the derivative of the second. The derivative of y is simply 1 dy dx. So 1 times dy dx. Actually, let me do it slower so you don't get lost. So let's do this as an aside. X times y is the same thing as f times g, and again that's the first times the derivative of the second plus the second times the derivative of the first. So that means that we have x times y prime, which is 1 times dy dx, plus the second, which is y, times the derivative of the first, which is simply 1. So here, what we have here is x times dy dx, as I began to write, plus y, because 1 times y is just y. And now we can actually put this together. So let's try to put this together. I'll start with the right side because it's easier to do. So it's going to be 100x dy dx plus 100y. And on the left side, we have 6 times x squared plus y squared times 2x plus 2y dy dx. And now what I will do is I'll actually take the 6 inside, since I don't want to deal with the 6 on the outside. So I'm going to have 6x squared plus 6y squared times 2x plus 2y dy dx equal to 100x dy dx plus 100y. And we're almost done with the problem. I mean, this is a more tricky problem than before. We're almost done with it. Shouldn't be scared by it. So let's see. Can I? Yeah, there's nothing to move, so I guess let's continue on. Yeah. All right. So let's continue to multiply. Multiply this out. So I have 12x cubed plus 6 plus 12 y x squared dy dx plus 12xy squared plus 12y cubed dy dx. That's equal to 100x dy dx plus 100y. Trust me, we're almost done with this problem. All right, so everything that has a dy dx is going to go to the left side. Everything that doesn't have a dy dx is going to go to the right side. So that means that this 12x cubed and this 12xy squared are going to go to the right side. This 100x dy dx is going to go to the left side. So I'm going to do that all in one step. So it's going to be 12y x squared dy dx plus 12y cubed dy dx minus 100x dy dx is equal to 100y minus 12x cubed minus 12xy squared. Now we factor, so we take out all the dy dx's. So that's dy dx times 12y x squared plus 12y cubed minus 100x equals 100y minus 12x cubed minus 12xy squared. Mind you, the calculus step ended a while ago. The calculus step ended when we took the derivative. Everything that we're doing now is just algebra. This is a y squared. And now we divide both sides. So we'll divide both sides by 12y x squared plus 12y cubed minus 100x. And we get 100y minus 12x cubed minus 12x y squared divided by 12y x squared plus 12y cubed minus 100x. Okay? So let's see. We could simplify this a little bit more. Yeah, we could simplify this a little bit more. I guess I'll keep it like that. I'll actually keep it like that. No, let me simplify. Because it's simple to simplify. 4 goes into all of these numbers. 4 goes into 12 and 4 goes into 100. So we get, I'm going to write the 100 terms first. So we get 25y minus 3x cubed minus 3xy squared. And in the bottom, we have minus 25x plus 3yx squared plus 3y cubed. And we could simplify this a little bit more. And the reason why I'm simplifying a little bit more is because we have to plug in a point to find the slope, and it's easier to plug in when everything is simplified nicely. We could factor out from the top an x, and we could factor out from the bottom a y. And we could write it like this: 25y minus 3x times x squared minus y squared. That's on the top, and the bottom we will have minus 25x, then plus 3y, and then x squared plus y squared. I factor out a 3x, a negative 3x from the top one. Did I take out the negative? And a plus 3y from the bottom one. And now we can actually find the slope, which is what the problem asked us to do way up here. So the problem asked us to find the slope at the point 3, 1. So we can now find it much easier with the simplified version. So remember, our coordinate point is given as xy, so this is at the point 3, 1. So we simply have to plug in on the derivative dy dx for x and y. So wherever you see a y, you put a 1. Wherever you see an x, you put a 3. This is going to be 25 times 1 minus 3 times 3 times 3 squared plus 1 squared divided by negative 25 times 3 plus 3 times 1 times 3 squared plus 1 squared again. All right. So what does this turn out to be? So this is 25 on the top minus, well, 3 squared is 9, plus 1 is 10, and then 3 times 3 is 9, and 9 times 10 is 90, so negative 90 will be up here. And then in the bottom we have negative 25 times 3, that's 75, negative 75. And then inside of the parentheses we have another 10, because again 3 squared is 9, plus 1 is 10, and then 3 times 1 is 3, so 3 times 10 is 30, so plus 30 in the denominator. And now we could actually simplify this even more. So negative 90 plus 25 is negative 65. Negative 75 plus 30, I believe today that's going to be negative 45. Notice that both of them end in 5, which means that 5 is a factor of both of them. And it turns out that negative 65 is 5 goes into it 13 times, and negative 45 is 9 times. And because they were both negatives, this last fraction is positive. So we found that the slope of 3 times x squared plus y squared equals 100xy at the point 3, 1 is 13 nines. So that's the slope at that particular point. Notice that this problem was not that difficult, to be honest with you. The most difficult part of the problem is taking the derivative in the top. Everything else is basically pre-calculus that we did, It's a lot of simplification and manipulations of the expressions. Actually, maybe I'm going to try to graph this in GeoGebra. I'll do it in a separate video. But this is a nice picture to see, if you're able to see it. Let me see if I can. No, I'll do it later. So let's do another example. Let's do another example. So let's say you're told to find the derivative dy dx implicitly for the equation sine of y equals x. Okay, sine of y equals x. So if you were asked to do this, then you have to take the derivative with respect to x on both sides. So for sine of y and for x. So you have to take the derivative on both sides with respect to x. Now the derivative of sine, we know from way before, it's just cosine. So this is going to be cosine of y. But remember, because we took the derivative with something with respect to that had a y in it, we have to multiply this by dy dx. And that is equal to the derivative of x. The derivative of x is just 1. So we have cosine times dy dx equals 1. But now we could divide both sides by cosine of y to get dy dx equals to 1 over cosine of y. Now, if we actually look at the graph of 1 over cosine of y, you will see that this looks like cosine but on its side. So the regular cosine wave, goes like this. This will be from 0 to 2 pi, right? So this is my x, this is my y. This is cosine of x. Now cosine of y will look something like this. Kind of look like this. Again, not to scale. So this is what cosine of y will look like. Again, it will kind of rotate here. And then at this point, you have negative pi over 2, and here you have pi over 2. Now what happens? Here we have pi over 2, and here we have negative pi over 2. If you restrict the domain of cosine of y, so this is cosine of y, if you restrict the domain of cosine of y to just be this point in blue, then you actually have a function. This is not a function because it fails the vertical line test at all of these points infinitely many times. But if you restrict the domain from y being between negative pi over 2 to pi over 2, then we do have a function. And we can actually write what that function is equal to. All right. Now, it turns out that we will see this again in the next section, so I don't want to spoil it for you, but we will definitely be seeing this very, very soon. Without further ado, though, let me just show you one more thing involving this. Remember, we had cosine squared theta plus sine squared theta. We mentioned that this was equal to 1, and this was a Pythagorean identity. Well, we know that cosine squared theta is equal to 1 minus sine squared theta when we subtract sine squared theta from both sides. Now, what you should notice is that the cosine of y is always positive on the interval y between pi over 2 to negative pi over 2. It's actually always positive. And it is 0 at the endpoint. So if we restrict our y's to these intervals, then we can actually do the following. We could take the square root here, the positive square root, so cosine theta is actually equals to the square root of 1 minus sine square theta. But theta here, this theta, is just a variable. We could actually change it. We could say theta equals y, and we could just change it for y. So we have cosine of y is equal to 1 minus sine square y, under the square root. But that is exactly what we have here, cosine of y. This is supposed to be a y, not an x. So we could actually substitute here. So we have the dy dx is equal to, instead of being 1 over cosine of y, it's 1 over what cosine of y is equal to, which is 1 minus sine square y under the square root. So again, we will see this further in the next lecture when we talk about the inverse trig functions and their derivatives. But I wanted to introduce this now to kind of give you an idea of what's going to be coming next. Because we find this inverse trig functions by taking the derivative implicitly. Again, what allowed us to use this substitution right here and go into this step was the fact that we restricted our domain to only the y values that are trapped between minus pi over 2 and pi over 2. Anyway, let's do a couple more examples, and that will be the end for this lecture. It turns out that you can actually find the second derivative implicitly. So let me just recall that we can take the derivative of a function more than once. For example, just recall, if you're given y equals 3x cubed plus 5x squared plus 5, then the first derivative of this will be 9x squared plus 10x. All right, that's the first derivative. Remember, this was what we call position. Then the first derivative gave us the velocity. And then the second derivative, if you recall, gives us the acceleration. So this will be the acceleration. So the first derivative again gives us the instantaneous velocity, and then the second derivative gives us the acceleration. So we can actually do the same thing. We could take the derivative of and get higher order derivatives of expressions that are written implicitly. So for example, if you're given, let's say, x squared plus y squared equals 25, and somebody told you to find the second derivative of y with respect to x, then when we differentiate this with respect to x, we have, let me just rewrite it here. So this is x squared plus y squared equals 25. So if you take the first derivative, we have 2x plus 2y dy dx equals to 0. And then if we solve for dy dx, we have 2y dy dx equals to minus 2x, which means that dy dx is equal to minus 2x over 2y. We divide both sides by 2y. And then the 2's cancel out, so dy dx is equal to minus x over y. Okay? So this is the first derivative. Now, if we take the second derivative of this, well, first of all, notice that we have a quotient. We have a quotient, f over g, which means that we have to use the quotient rule. And if you don't remember the quotient rule, I'll remind you. It was the bottom times the derivative of the top minus the top times the derivative of the bottom squared. Or alternatively, I told you that you could use the chain rule instead of the quotient rule if you bring the denominator to the top. So you could also do that. In any case, I'm going to use the quotient rule. So let's f of x be negative x for the top, and let g of x be equal to y. Then the derivative of f is simply minus 1, and then the derivative of, this is g of y, the derivative of g is going to be 1 dy dx, because we took the derivative of an expression in terms of y with respect to x. So now we put this formula together to take the second derivative of this. What do we get? Well, we get that the first, which is g of x, that's just y. So we get y times the derivative of the first, which in this case we said that was minus 1, minus, from the formula, f of x, which is minus x, times the derivative of g, which is dy dx, all over the denominator square. So that's g, which is y squared in this case. If we put this together, we have minus y, and minus is plus, so minus y plus x dy dx over y squared. But now, could actually do something very clever. We know what dy dx is equal to. We found what dy dx is equal to. dy dx is equal to negative x over y. So we'll actually substitute it here for where we have dy dx, because we already found that. So we have minus y plus x, and dy dx is minus x over y, so times minus x over y divided by y squared. And now what do we have here? We have minus y minus x squared over y divided by y squared. But now what we can do here is simply do the keep change flip method. So here we have minus y minus x squared over y divided by y squared is the same thing as minus y minus x squared over y times 1 over y squared by the keep change flip method. This is a binomial times a monomial. So when we multiply each term. So when you multiply 1 over y squared times negative y, you get negative 1 over y. And when you multiply this one, you get negative x squared over y cubed. Okay? Yeah, negative x squared over y cubed. Yeah. And now let's combine these two fractions. So to combine these two fractions, I have to multiply by what's missing. So I have to make the denominator into a y cubed. So to make the denominator into a y cubed, I have to multiply by what's missing, and what's missing here is a y squared. When we multiply fractions, we multiply across. So I will have in the top minus y squared minus x squared divided by y cubed. If I take the negative sign out from here, I have minus y squared plus x squared over y cubed. And trust me, we're almost done with this problem. We know what y squared plus x squared is from the beginning of the problem. X squared plus y squared was equal to 25. This is a radius, a circle is radius 25. So it's actually equal to minus 25 over y cubed. And that's the end of the problem. So we can take the derivative multiple times of an expression that's given implicitly. And notice that we were clever. Here, to simplify more, we substituted for what we knew, which was that dy dx was equal to negative x over y. And the same thing here. Here we simplify by something we knew, that y squared plus x squared was equal to 25. If you wanted to, you could take the derivative of this a third time. So if you were to take the derivative a third time, if we were to find dq of y dx cubed, then, you know, if you rewrite this as minus 25 times y to the minus 3, then when you multiply minus 25 times negative 3, you're going to get 75. And then you minus 1, so that's y to the 4th, so that's 75 y to the 4th. And then you could keep on going, you know, you could keep on finding the derivative implicitly. So this is a third order derivative right there that we found. Okay. Let's move to the next example. Now, much of this class is devoted to finding the equation of tangent lines, and it should be no surprise that we can actually find the equation of a tangent line of an expression that's given implicitly. So let's find the equation to the tangent line. At the point square root of 2 over 2, comma, square root of 2 over 2 of the graph given by x squared times x squared plus y squared equals to y squared. Okay, so let's see what we have here, what we're dealing with. It doesn't hurt us to actually multiply this n. So we could FOIL this or distribute this to the inside. I don't think that will hurt. So we have x squared times x squared, that's x to the fourth. Then x squared times y squared is just x squared plus y squared. That's equals y squared. And then to make our life even easier, we could bring this y squared term to the left side, because we know that eventually that's going to have a dy dx, so we might as well deal with it now. It's supposed to be y squared minus y squared equals to 0. So what did I do here? I first distributed, and then I moved the y squared term to the left side. Now I'm ready to find the derivative of this with respect to x. So now we could say d dx of x to the 4 plus x squared y squared minus y squared is equal to d dx of 0. So the derivative of 0 is just 0, and then the derivative of x to the fourth is simply 4x cubed. Now in this middle portion, we have to use the product rule. So I'm going to do this. I'm going to write simply f times g here, because we're going to do it on the side. And this is something that you should always do. Whenever you have something like this, like a product rule, a quotient rule, or a chain rule, put a placeholder and then do that on the side, because it could get very convoluted when you're doing this. And minus the derivative of y squared. Remember, we take the derivative as we normally would. We just make believe that there is an x here, so that's 2y, and then we multiply by dy dx. So all we have to do is find the derivative of the product. So I'm going to do that on this side. And again, let's remind ourselves, this is first times the derivative of second plus second times the derivative of first. So that means that we have, if we left f be x squared, so we have x squared times the derivative of the second is 2y dy dx plus the second, which is y squared, times the derivative of the first, which is 2x. So let's put this together. That means that we have dy dx is equal to, well, I don't have dy dx yet. We have that this d dx, or this expression, is the derivative, is equal to 4x cubed, and then plus f times g. Well, f times g is 2x squared y dy dx. That's this first piece, plus 2x y squared minus 2y dy dx equal to 0. And now we can move every term that doesn't have a dy dx to the right side. So this is the same as 2x squared y dy dx minus 2y dy dx equal to minus 4x cubed minus 2xy squared. Now we could factor the dy dx. So we factor dy dx out of this left side, and we have 2x squared y minus 2y equals to minus 4x cubed minus 2xy squared. And then we divide both sides by this factor right here. So we have dy dx is equal to minus 4x cubed minus 2xy squared divided by 2x squared y minus 2y. Now, remember that we're trying to write the tangent line to this equation, and we're given the point radical 2 over 2 comma radical 2 over 2. That's our x, this is our y. So, sometimes it is easier to try to factor as much as possible. So let's see what happens if we do try to factor a little bit. So let's see, dy dx, we could factor at 2x from the numerator. So I could actually factor a negative 2x from the numerator, and I have left 2x squared plus y squared in the top. And the denominator, I could factor out a 2y. So I'll take out a 2y, and I'll be left with x squared minus 1. Let's see, does that work? Yeah, that works. X squared minus 1. And now, you can see that there's some cancellation here. We have minus x, 2x squared plus y squared on top, divided by y times x squared minus 1. Yeah, that seems correct. All right, so now we have to evaluate this at the point radical 2 over 2 and radical 2 over 2. So let's plug in. So I'm going to continue on this side so I could have more space. So I have minus radical 2 over 2 and a minus on the outside. That's because of this first x is negative, times 2 times radical 2 over 2 squared plus radical 2 over 2 squared divided by radical 2 over 2 times radical 2 over 2 squared minus 1. Okay? So let's simplify this a little bit. Negative, negative is positive, so this is radical 2 over 2. Actually, let's simplify that even faster, because we have minus minus cancel out, right? And then we have radical 2 divided by radical 2, that cancels out as well. So we're in very good business right now. So you just have to worry about the things on the inside of the parentheses. But notice that if you have something like this, radical 2 over 2 squared, the square goes for both of them. So this means that we have radical 2 squared and 2 squared, but radical 2 squared is just 2, and 2 squared is 4, so this is 2 over 4, which is 1/4. So whatever we have at radical 2 over 2 squared, that's just 1/4. So what we really have is 2, meaning this 2, times 1 over 4, that's 1 over 4, times 1 over 2, not 1 over 4, because 2 over 4 is 1 over 2, times 1 over 2, plus 1 over 2, because of this one, divided by 1 over 2 plus 1, because of the minus 1, because of the denominator. Minus 1. So now we have well, no, this is good. This is good. Unless I had it. So now 2 times 1/2 is just 1. So we have 1 plus 1/2 in the top and 1/2 minus 1 in the bottom. Now, 1 plus 1/2 in the top is the same thing as 2 over 2 plus 1 over 2, which is 3 over 2. And then in the bottom, we have 1/2 minus 1 is just minus 1/2. And this is a complex fraction, so this is equal to 3 over 2. You know, you can multiply this by negative 2, which is eventually what we will do. This is, 3 over 2 divided by negative 1 over 2, the same thing as 3 over 2 times minus 2 over 1, which equals, this cancel out, so this is equal to negative 3. So we have m equals negative 3. All right, so now we can actually write the equation of the tangent line, because remember, to write the equation of the tangent line, we do y minus y1 equals m times x minus x1. And we have a point for x and a point for y. So we can just put it together. So we have y minus square root of 2 over 2 equals minus 3 times x minus square root of 2 over 2. I'm not going to simplify this any more than that. I mean, I guess I could. I could move it over. Yeah, whatever. I'll do it. So minus 3x plus plus 3 radical 2 over 2, and then plus radical 2 over 2. And then if you want to, you could combine those. I'm not going to do that. But you could. You could definitely do that. Because you have, fine, I'll do it. Minus 3x, and then you have 3 radicals 2 over 2 plus 1 radical 2 over 2. That's 4 radicals 2 over 2's. But 4 divided by 2 is 2, so this is y equals minus 3x plus 2 radical 2. And that's it. That is the equation of the slope of the line. So that's what she wrote for this problem. Finally, this is last example, and call it a lecture. Taking the derivative of logs, so log differentiation. I gave you some rules about logs. Earlier we definitely spoke about the natural logarithmic function. So recall, if you take the derivative of something like ln of x, then that's equal to 1 over x. And if you take the derivative of ln of u, that is equal to 1 over u times u prime. So we definitely saw this before. So sometimes you may be faced with taking the derivative of something with logs with respect to x. So for example, if somebody in the bus comes up to you and tells you to find the derivative of y equals x minus 2 squared divided by x squared plus 1, and they also tell you that x is not equal to 2, so they also give you a piece of paper telling you this, then we're in business. We could actually take the derivative of this implicitly. So let me rewrite. This is y equals x minus 2 squared over radical x squared plus 1, and you're told that x is not equal to 2. Why is x not equal to 2 important? Because it means that the numerator is never going to be 0. Because if x equals 2, then the numerator is 0, which means that y eventually can be 0. In the denominator, x is being squared, so we're adding 1 to it. So no matter what number we pick for the denominator, we're never going to have a negative number, which means that the square root domain is satisfied, and the denominator is never going to be equal to 0. So b is never equal to 0. X is always positive in the denominator. In fact, yeah, x is actually bigger than or equal to 1 in the denominator. So, I mean, this expression is bigger than or equal to 1. Doesn't matter. So we're in good business because if this is the case, then we could actually take the natural log of both sides. Remember, the natural log function, when you graph it, looks like this. So it has an asymptote when x is equal to 0. But now we know that this is actually going to be completely defined in terms of y. So we could take the ln on both sides of this and then take the derivative. So if we do the ln of y, that's equal to ln of x minus 2 squared divided by square root of x squared plus 1. So that's the first thing that we can do to find the derivative of something that looks like this. Now, because of the rules of logs, which remember I gave you this a couple of lectures ago, we could break this up a little bit more. So first thing I will do is write this as ln of x minus 2 squared minus ln of x squared plus 1 to the power 1/2. Okay, I just rewrote the square root to the 1/2 power, because now, again by the rules of natural logs and logs, I could pull out the 2 to the front, the exponent. So this is 2 times ln of x minus 2 minus 1/2 times ln of x squared plus 1. And now I could actually take the derivative of this term by term. So ln of y is going to be what I have up here. It's going to be 1 over u times u prime, meaning 1 over y times dy dx. Instead of writing dy dx, though, I'm going to write y prime. So recall, y prime is the same thing as dy dx. So instead of writing dy dx, I'm going to write y prime. So I'm going to have y prime over y, because if you have 1 over y times y prime, you multiply across, so this is y prime over y. And that is equal to 2 times the derivative of ln of x minus 2. Well, what is the derivative of 1 of ln of x minus 2? It's simply 1 over u times u prime, but u prime here is going to be 1, so it's going to be 1 over x minus 2 and times the derivative of that, of the inside, which is just 1, minus 1/2, again, times the derivative of this piece right here. And that derivative is going to be 1 over x squared plus 1. And by the chain rule, we have to also multiply by the derivative of the inside, which in this case is 2x. So we have that y prime over y is equal to 2 over x minus 2 and minus, well, the 2's cancel out here. So we have x on top and x squared plus 1 in the bottom. Okay? And now, if we want to make the denominators the same, what do we have to do? Well, we have to multiply by what's missing. So what is missing on this side? Well, we're missing an x squared plus y plus 1 term. And on this side, we're missing an x minus 2 term. So I'm going to multiply top and bottom by the terms that are missing. So x minus 2 is missing here. So I'm going to multiply top and bottom by x minus 2. And then on this side, I'm missing x squared plus 1. So I'm going to multiply top and bottom by x squared plus 1. So that means that I have y prime over y equals to, let's see, that's 2x squared plus 2 minus x times x is x squared, then minus x and minus 2 is plus 2x. And then in the denominator, we simply will keep that the same, x squared plus 1 times x minus 2. Let's simplify this a little bit more. If we simplify this, we have 2x squared minus x squared is simply just x squared plus 2x plus 2. And the denominator, we have x squared plus 1 times x minus 2. And finally, we can actually cross multiply. So let's see. Oh, actually, it's actually even simpler than that. Here I'm dividing by y, so I'm solving for y prime here. So the opposite of dividing by y is to multiply both sides by y. So I'm going to multiply both sides by y and I'll be done. So this is going to be y prime equals to y times x squared plus 2x plus 2 divided by x squared plus 1, x minus 2. If we wanted to, we could actually continue to solve this because we actually know what y equals. You may say this is a very long problem. I will agree with you, but we actually can find the solution because we know what y equals. Y is equal to x minus 2 squared divided by square root of x squared plus 1. So if we wanted to, you could say y prime is equal to, and actually it's equal to y, but in this case y is equal to x minus 2 squared divided by square root of x squared plus 1, and you're multiplying that by x squared plus 2x plus 2 divided by x squared plus 1 times x minus 2. So as you could see, at least one of the x minus 2 terms are going to cancel out. And then you're going to have some nice things happening in the denominator. So let me see if I can simplify this a little bit more for you using this gray. So the x minus 2 is going to cancel out with this x minus 2, and I'll be left with just one x minus 2 term in the top. This radical x squared plus 1 is to the power 1/2 times this x squared plus 1, which is to the power 1. You have the same basis, so we add up their exponents. 1/2 plus 1 is 3/2, so this is going to be x squared plus 1 to the power 3/2. And we didn't do anything with the x squared plus 2x plus 2 terms, so we'll keep them up there. And that's as much as we can actually simplify. I mean, you could FOIL this, but it's not going to help us out much. So this is implicit differentiation. It's going to be very useful as we move forward, and you will see it in more detail in Calculus 3. So for those of you who are majoring in mathematics, you will eventually see in Calculus 3 something called partial derivatives. And the idea of implicit differentiation, which we know comes from the chain rule, is also explained in Calculus 3 with partial derivatives. Thank you for your attention.